So today we go into chapter 6, which is deal with mechanical behavior. So we will deal with material properties that you can test, you can pull, and so on. So this one is also part of your lab, experiment. So we'll look at what mean by plastic deformation, what mean by yield stress, tensile strength, ductility, and so on. Okay, yeah. So we in this chapter we will learn all these things. We learn all these things. We go through one by one. Okay. So we do by looking at, before we look at the properties, we look at the process, right? What usually the process involved with metals and alloy. So the first one is casting. Casting. So in the casting, we need mold, which is a case to form the outer shape of that products. So on the diagram here, this is called permanent mold. Right? There's a mold. This is one type of the mold. We have a few types. First type is a permanent mold, means the shape doesn't change. The mold, the casing outside doesn't change. So when you pour inside the liquid metals, right, the molten liquid, you pour from the top, then you will fill all the gap here. Sometimes you need pressure pump from the top, and then you push all the molten to fit all the gap here. So they are designing a mold also part of the expertise if you want to go into, and that one is very technical, right? As an engineer, so your job is to design the mold, right? So not under this designing the mold, not under this module. So just this module just tell you that what are the process. Okay. So if you use a mold and do casting, the product is called cast product. The one that you take out from the mold is called cast product. For example, your car piston, the piston that you seen in your automotive, right? So there's a video here. So how the cast molding process. So this is the permanent die cast. So they will fill in. This is another one. So they will fill in the assembly. This worker is assembly the mold and all the valve and so on. Then you pour in the molten metals. Again, this video show you the very simple component. You can go into very complex component. If you see, this one is aluminum product. Then you try to break the permanent mold. Nowadays, we already have a 3D printing technologies, including 3D printing metals. Now, even we have a printer for biomedical, right? So 3D printing is part of the alternative in replacing the die cast method, right? Okay. Okay. So the first one we already tell you the die cast. So previously, in the previous chapter 5, we do go through the solidification process. Just now we introduce you the die cast. The solidification process previously in a mold, we tell you type of the grain that you have. On the wall here, you have a uniform grain on the wall. But at the center here, you'll get a longitudinal, a long shape of grain. So this one is part of chapter 5. So This one also will tell you the structure or the properties of that one. Then we introduce you the second methods of processing metals is called rolling. So you have two type of rolling. One is hot and one is cold. So normally when we do rolling, the end products is a plate, a metal sheet. You roll, right? It's like yeah lah. If you're good in cooking, you have a roller, means you make the dough become thin, right? So same process in the metal rolling. Okay, so on the screen here is by process where how the process make the ingot, where the ingot becomes thinner and thinner. So process one, you have a roller with the gap, maybe gap 1. So you go through here, you press the metals a little bit. Then second process, this one is rotate in and out, right? So this one you go in, then the machine will press in again and then roll back. Then process 3, the roller get closer, then repeat the process until you get a very thin products. Okay, so to to have this one, the process, the one that you see here is under hot rolling. So when you know the metal, when they hot, they able to form. It's more easier to form. Okay. And this is a large scale operation that you see in a big factory. It's the same process, but this is a continuous process, as you can see in the middle diagram here. So you start from the right and then go through the process, right? As you go through the process, at the end of process is the thickness that the customer want. So this is example of cold rolling. Cold rolling. Cold rolling means you do it in the low temperature. If you see the word cold rolling or cold working later, this is rolling. The word cold means you do it in a room temperature. Do it in a room temperature. So same process, is just that the temperature is different. So we have hot rolling and cold rolling. To define hot rolling, we develop from cold rolling. Cold rolling is at room temperature. What I mean by hot means above room temperature. Later, when you study about phase diagram, there will be a phrase called recrystallization. Okay, so cold rolling, they are carried out below the recrystallization temperature. Okay, so this one, it will make the strain hardening. It will create it will help the metal become stronger. So there's an equation for cold rolling. We interested in percentage of cold reduction. We take initial thickness minus final thickness divided by initial thickness times 100%. Means initial thickness, initial, you take output, initial minus output or final, right? Why we take initial minus output or final? Because when you do cold rolling, the thickness before will be bigger than the thickness after. Sorry. Okay. Or Change 1 down to F. So you get a positive percentage. Okay. Quite direct, quite direct means if the question asks you to calculate percentage of co-reduction, you need to, if you're given percentage of co-reduction, you can calculate the final product or the initial products. Normally the question will ask you the initial value. I'll tell you the customer order such and such thickness, and then the factory machine was set to maybe 5% or 10% co-reduction. Calculate the initial thickness that needed in this process. So you use this simple calculation. So this is a quick question. So for example, calculate the percentage of co-reduction in cold rolling. Aluminum sheet from 3.048 mm to 3 point something to 1 point something mm. So how many percent of co-reduction? Can you calculate it? You should be able to do this simple calculation. How many percent? 6. What other answer? What's the percentage of co-reduction? When you go to work later, if you work in the American company or Europe company, they most of the time you see imperial unit. But if you are producing some of the UK products, then you will see MM. So how many percent? 60 something. Okay. So 66.7%. So practice again. If you're given a sheet of alloy, now you have two kind of alloy. Alloy means a mixture of more than two elements. So you have 70% copper and zinc. They are co-rotated 20% to a thickness of 3 mm. The sheet is then further co-rolled to 2 mm. What is the total percentage of co-roll? You have two processes. One, you go through 20%, you get 3 mm, and then you further co-roll again. Process number 2 into 2%, into 2 mm. So what is the total percentage of co-roll? Same, you pull the calculation. Percentage of co-reduction, you take initial thickness minus final thickness divided by initial thickness times 100%. So you need to calculate the starting thickness first, right? So starting thickness is initial minus final. Final is 3 divided by initial thickness times 100%, or the ratio is 20%. The co-rotor is 20%, so 20% is 0.2. So you get the X, right? So what is the X from this? Okay, so the initial thickness is 3.75, right? Then you calculate the total, means you start from the initial until the end. So you take 3.75 minus the final one is 2 divided by 3.75. Then you get how many? Okay, 46 point something. All right. So this is how you do the percentage of co-reduction. This equation always interested in looking at the initial and the final. Initial and the final, right? So don't confuse like, oh, I have 2 or 3 process, then I don't know how to calculate it. Always interested in initial and the final product. Unless the question asks you, station 1, how many percent? Station 2, how many percent? Station 3, how many percent? Yeah? Understand? Right? So unless the question asks you in a few stations, let's say this is station 1, station 2, station 3. So it might ask you how many percent of co-reduction here, co-reduction here. Then it might ask you from here to here, how many total co-reduction. Okay, you look carefully on the question. So this example 1 is ask you the total, means from the start until the end. If the question modified a little bit, it gives you a few stations, then it asks you how many percent, calculate co-reduction for each station and total reduction for the process. Means you need to calculate 4. For example, the one that I draw on the whiteboard here. You have 4 calculations. If the question asks you to have 3 stations and then asks you the total reduction, so you calculate 4 calculations. Okay. Another one process is called extrusion. I'll show you. Maybe the screen is not very clear. So extrusion is a plastic formation. It's a plastic formation. Before I go into this, I'll give you an early introduction what is plastic. So previously, if you plot stress versus strain graph, again, what is stress? Stress equal to force divided by area. And previously, I draw one diagram. What is stress? Is when the force is perpendicular to the area. This is force, this is area. So when the force is perpendicular to the area, then it forms a stress force. Okay. So when the force is parallel to the surface, when the force is parallel to the surface, it will form shear stress. Also stress, but it becomes shear stress. Shear, shear stress, when the force is go parallel to the area. Okay. Becomes shear stress, still you get force divided by area. Then another one is called shear stress. Yeah, okay. Okay. You have a tensile stress and shear stress. So if you plot stress versus strain, okay, what is strain? Later we will still look at this diagram. What is strain? Strain is the deformation. It's a change of length normally. It's a change of length. In 2D, in 2D, 3D, it become later. I'll give you one formula. But we are looking at strain. This is strain, strain. Strain is the change of length divided by original length. So for example, you pull, then it become longer. Let's say you fix the end, then you pull. So you take the total length, total deformation, the length change divided by original length. So if you plot the graph, let's say we have an ideal case, you will have a straight line on the tensile graph, right? If you get a straight line, what does it mean? It means you're in the elastic region where you pull the metal and then you let go, the metal will go to original size. This region is called elastic region. Elastic region. Then you will reach to a point where the elastic region fade away, right? So it will change to plastic formation where you see like a quadratic curve. This is called plastic. Plastic is like a bubble gum. You pull, but it can no longer go back, but it still can pull, not yet broken, but it still pull, but you let go the force, it will stay at that length. So that one is called elastic or plastic. Sorry, that is called plastic, not elastic. And then after plastic, it will fracture or broken. It will we use fracture. So it will break away in two pieces. So the one that you see on the screen here is the extrusion. Extrusion means you're working in the plastic region where you pull the metals. Okay, you pull the metals under high pressure. Extrusion, the word always linked with the cross section of the ingot or the products. So it's a reduction of cross section through an opening of a die. Okay. So since it's pulling through a die or opening of a die, the products that you can produce by extrusion process, normally they have a shape that you can form by the opening of the die, right? Let's look at this video. This is a die that push inside. So this is the product at the other side of the die. So you push, this is a die, and then you come out with the final products. See on the diagram, if you try to force the metals go into the opening of the mold. So if you're a designer of the mold, be careful on the sharp corners, and you need a lot of lubrication in the mold, and you'll create heat also. So you have two types of extrusion. You have direct extrusion and indirect extrusion. On the left is direct extrusion, where you see there is a billet. It is the raw material. There's a ram forcing the billet into the die, and then you have extrusion products. So this is called direct extrusion, where you straight away you get the shape that you want. On the right is indirect. As you can see, the ram is opposite direction of your end products. This is the billet, the ram and the mold pushing from the left. This is the closure plane. So as you press the ram, the billet is squeezed opposite direction of your ram direction. This is called indirect extrusion. So you have two types. If you're defining the direct extrusion, means the direction is parallel and same direction with your ramp. It's fall under direct extrusion. If it's under indirect, means your extrusion products is opposite direction from the ramp. Okay. So how do you decide whether you want to use direct or indirect? Most of the time, it's based on the factory floor space that you have. Right. So indirect, you will save some space compared to the direct case. Direct one, you need a long space there. Right. So this is another video that show you how aluminum cast and extruded. Right. Let me see. So we won't go through all because this is a 12 minutes video. So this is a full-scale factory floor. You go and watch this video, right? So another one is called forging. Now, just now what we have gone through, we've gone casting, we have gone through extrusion, we have gone through rolling, hot rolling, cold rolling, and there's an equation for cold rolling. Now we go into forging. What do I mean by forging? Forging means you press it or you hammer it to a desired shape in a hot condition. Okay. So the keyword for forging is you imagine the shape of a hammer. Right? You bang the products. Okay. So there are two major methods. Either use hammer to hit the products, or you use press forging. So let's look at this animation. This is open die. You have a piston on top. There's a column, then there's a hammer in the middle. Then it will go down and hit the products. So the die will have the shape that you want. Then you're going to hit the things. You have a top die and bottom die. Just now it's an open die, now it's a closed die. The column, lamp, the top die, the cavity, bottom die. You put in a hot billet, then you hammer it. Okay. This is a press forging. Just now before this one, this two is a hammer. This is press. You look at the die shape and the products. Okay, so there are two type of one is hammer, one is a press forging. So we have seen what is open die, what is die forging. Open die normally it was used for a large part size compared to closed die forging. So these are the basic shape of open die. We have flat until the V dies. For the closed one, you have top and bottom, right? Normally it will be a smaller size. The product will be smaller size, including the billet also, right? The new technical word for today, billet. So the practicality of forging is to create irregular shape compared to casting. Okay, compared to casting. So by looking at the end product, you should able to predict what are the process involved, right? So for example, the casting, rolling sure come out with a flat sheet, right? Then pressing, forging, and so on. Huh? This is a wire drawing, how the wire was processed, right? I give you the animation one because it's better, give you the better illustration, right? One type of a metal forming is a wire drawing, right? Wire drawing. So it's the same as the extrusion, but it's a continuous extrusion, right? The end product is in the wire shape. Okay, let's see how the. So again, it's still extrusion, but the end product is in the wire form. The smaller diameter you need, the more station that you. It's just a repeated extrusion. The round body here is because you want to slowly, don't want to destroy the properties. You want to slowly pull it and then cool down, pull it and then cool down. This is in industry on the wire machine just now. So just now is the animation. This is on the factory floor. This video is from the end until the beginning. This is the end products, and then it go back to the early process. This is a China company. So this is one of the station. It do spinning, and wire was extrude here. Then he roll the products. Then this is a whole station. The further back is more thick. The diameter is bigger and bigger. Okay. So we are now in a IoT, Industrial 4.0 already. So most of the process here will be controlled by computer. So if you are a technician who is doing manual, then you might out of job because we no longer need person to monitor the things already. We have all the sensors to see the process. Okay. Okay. Then we have another one called deep drawing. Just now it's a wire drawing. Now another process is called deep drawing. As you can see on the diagram here, there is a punch from the top, and then there is like a mold here. You will see this one when you work in the metal stamping company. I work as a project engineer in the precision metal stamping, where we form the outer case of the hard disk. You know, the hard disk, if you open the hard disk, there is a shape going in. So that is using drawing process. In this case, you punch down, then you get the shape of that particular spec that you need. Deep drawing, you always start with a flat sheet, a flat slit, then you punch down to get the shape. Okay, we will stop here, or you can continue. Continue, can All right, we go into mechanical properties already. Yeah. So recap, how many process that we have learned so far? How many? First one, start with. We start with cold rolling. We start with casting, right? Casting, then cold rolling, casting, lowering. You have two, right? Hot and cold. And cold rolling, you have one calculation for percentage of cold rolling. Then what else? Extrusion. Extrusion, you have how many type? Direct, indirect, correct. Then continue. Forging, yeah. Forging, you have how many type? Two type. One is hammer. Press. Correct. Hammer press. And then one more. Then forging, what do you learn? Wire. Wire what? Drawing. And then continue with deep drawing. Okay. So all these process will give you different shape. Different shape. You can have a hollow. You have a piston cap, and so on. All right. So, and you have a wire shape. Then you have a box shape, something like that. Right. So by looking at the final products that you have, you can predict what kind of process involved. Okay. Next, we look into mechanical properties already. We look at stress and strain. First one, we will introduce you the elastic and plastic. So this one, we already introduce you like what I draw on the whiteboard here. The first term is called elastic, where you see on the diagram here. The process 1, process 2, process 3. Process 1, let's say you have a sample and you pull with the force here. What type of force you have? You have a tensile force. You have, okay, how many type of force that you have? How many force that you have? First, if you pull at the both end, perpendicular to the area, cross-section area, this is called tensile loading. And if the force is pressing into the surface, it's called compressive force. If the force go parallel to the area here, or cross-section area, is called shear force. It can be this way. Shear always opposite one. Okay. Look at this one first, then later we look into more complex one. So what are the keywords when we talk about elastic? Okay. Elastic means it can go back to its original shape. The keyword is it can go back to original shape or recoverable deformation. It deformed, but it recoverable. And nowadays we talk about smart material. Smart material actually it revive the elastic behavior. Means you do and then you have a memory inside the design, so it will fall back to the original shape. Plastic deformation is the one that you see on the simulation on the right hand side. So if you press down and then you remove the force, the object will remain in its final shape. This is fall under plastic deformation or permanent deformation. Okay, so you have two types of deformation: elastic or recoverable deformation. Another one is called permanent deformation or plastic deformation. Two types. How deformation works? Deformation is produced as a result of your force or load. Force or load. So there are many types of load or force. I've introduced you the tensile force. I've introduced you the compressive force. I introduced you the shear force. There's two more: torsion and bending. What I mean by torsion? Torsion means you twist the products. You twist the product. This one become torsion. Okay, when you twist, it gives you torsion. Or in static, you've learned static, right? How torsion give you? By result of moment. Right? What I mean by bending? You have two datum. If you press from center, it will bend. Right? And you will learn about this one if you study structure analysis. You will learn about IXX, IYY, IZZ. Have you seen this one? Not yet. Not yet. Okay. There's a formula to calculate the deformation on the structure. There's a formula, and if you change the datum, there's a don't worry. If I teach you this subject, not engineering, but I teach you related to finite element analysis or other subject, you always have a table, a standard table, right? Because you're being trained as engineer, right? So you need to refer to the correct graph or table. So on the table, you look at the case, you refer, there's a formula there. You just use that one and calculate. Okay. So these are the diagram that you will see. So tension, compression, bending, shear, torsion, or combine. When you want to cut metals in the process, in the industrial process, normally you will use shear. Even you use scissor to cut paper, the force that you apply to the paper that you cut is called shear loading or shear stress. Okay. And the shear force, sometimes if you if you prepare the metals not correctly, especially when you do with pure metals and so on, some metals they are easily broken by shear loading. So just be careful on that, right? So this shear loading, we will handle this one by the last few chapter when we go into composite. Okay. And I introduce you before this, what is the meaning of stress? Stress means you take force divided by cross-section area. Cross-section area, where the area meet the force. Okay, meet the force. And then I also introduce you the strain. Strain is the change of length. You take the change of length divided by the initial length. It gives you strain. So engineering stress, how you calculate. We are interested to look at initial area, cross-section, and the initial length. And then in this case, you see the two blue arrow pulling both end outside. So it gives you a tensile loading or tensile force. Okay. And with this tensile loading of force, it will give deformation. So you have two types of deformation just now, elastic and plastic. Recoverable or permanent. So in this case, we don't know yet, right? So the first equation, okay, there's one word here on the screen here, uniaxial. Uniaxial tensile force. It just means that if you draw a cube, you have forces at three axes, x, y, z, right? X, y, z. So uniaxial means you have same force acting on all the direction, right? But sometimes we just remove the thing and then we just focus on one direction. It's called uniaxial. All right. So uniaxial you can just assume as a one direction force that go through the center of the object. Okay. So the first one is called engineering stress. And if the stress is perpendicular to the cross-section area, another name for it is called normal stress because it's perpendicular, right, or normal direction. So you take force divided by area. Okay. Okay, I draw something on the whiteboard. Let's say you have a cube, a rectangular cube, acting by a tensile loading force. Look carefully on the surface that I've highlighted. This cross section will give you stress. Will give you stress or normal stress because the red arrow is perpendicular to the area. I'm going to highlight another area. This top area will give you shear stress. Same symbol, but you have a shear sub there. Okay, why this one shear? Because the arrow of red arrow parallel to the cross-section area. Or I drop the cross-section area here parallel to the force. I still get this area. So be careful on whether you're finding normal stress or shear stress. Same loading, but I give you different stress. One is normal stress, same normal stress, but the effect of the loading, it will give you another effect called shear loading. The unit for normal stress, Newton over meter square. Force unit is Newton, area is meter square. So the combination of dimension is Newton meter. Newton meter square. Right. So if you do conversion, pound per square inch, there's a conversion. But in our module, we'll use unit SI. So let's do a calculation for tensile or normal stress. You're given 12.7 mm diameter of aluminum bar subject to a tensile force 11120 Newton. Calculate normal engineering stress in Pascal on the bar, in Pascal, PA, or Newton over meter square. So what is the answer? So what's your calculator tell you? How many Newton over meter square? Okay, when we find this one, we have a break. What is your answer? Who haven't signed? Tan Kai Shen, are you here? Are you here? Sign attendance. Okay. So what's the answer? Huh? 6.89. What is the unit? Unit Pascal. Huh? Do you agree? Do you agree? What's the formula for Pascal? Stress. What I mean by stress? Okay. F divided by A. So remember to change the unit into meter before you do calculation. For this module, normally we will trap you with unit. If it come in mass, we normally give you megagram. In length, normally we'll give you centimeter or micrometer. All right, so you substitute, you get 8 point something, not 6 point something. Huh? Huh? What is the shape of the object? What is the shape? Is this a rectangular or tube? Huh? You read the question carefully. What mean by diameter? Diameter is a round shape. What is the area of a round shape? R square or pi d square over 4. Right. Correct. Your R equal to d divided by 2, right? So that's why the answer there you see pi divided by 4. Of course, you can directly calculate pi r square. You need to divide the diameter into half, 6.35. if you use pi r squared. Okay, stop here. Let's see, huh? Okay. Okay, stop here, we continue. We have 10 minutes breaks, we continue 9:10, huh?